To build a working quantum computer, scientists have to create one of the coldest environments in the known universe. The processing chips sit inside complex structures that look like golden chandeliers, chilling the hardware to a fraction of a degree above absolute zero. These ultra-cold machines are incredibly powerful, but to solve massive problems, they can't work entirely alone. Eventually, they must connect with other quantum computers to share information and divide up the work. Inside that freezing environment, the quantum bits, or qubits, communicate with each other using tiny pulses of energy called microwave photons. You can think of it a lot like the Wi-Fi signal routing through your house, just infinitely smaller and much more fragile. The problem is getting that signal out. If we try to send a delicate microwave pulse out of the deep freeze and into a room temperature cable, the heat and ambient noise instantly overwhelm the data. It's like trying to move a single snowflake across a hot desert. The heat erases the information before it can ever arrive. Because of this temperature barrier, these incredible machines are trapped. Without a way to safely move their signals through the warm outside world, superconducting quantum computers remain permanently isolated, making a larger network impossible. To get the information out, researchers realized they couldn't just add more insulation to the microwave pulse. Instead, they had to translate the data into a completely different form of energy that could survive the heat. The solution they developed is a tiny device that sits directly inside the cold environment, known as a microwave to optical transducer. This device acts as a specialized quantum translator. It catches the delicate, low-energy microwave signal from the qubit and converts it into a high-energy particle of light, known as an optical photon. This photograph shows why light is so useful here. These are standard glass fiber optic cables, the exact same kind used by telecom companies to bring broadband internet to your neighborhood. Light doesn't care about room temperature, so it can travel safely through these glass threads for miles without the data being lost to heat. The transducer acts as an essential bridge. By turning the fragile quantum information into a beam of light, it gives the data a protective shell, allowing it to safely leave the freezing environment. This schematic shows how we use that light to connect two machines. On the far left and right, we have two separate quantum computers, marked qubit A and qubit B. Both computers simultaneously translate their microwave signals into optical light and send them down those red fiber optic cables toward a central meeting point. If you look right in the center where the red lines cross, you'll see a blue diamond shape. This is called a beam splitter. It is a physical crossroads where the two incoming particles of light mix together. Above that blue diamond are two gray detectors. Because the light is so perfectly blended, the detectors can't tell which photon came from which fridge. Any record of their original journey is completely lost, and the particles become effectively indistinguishable. This is the crucial moment. Each particle of light started its journey perfectly synced with its home qubit. When we force those two light particles to mix so thoroughly that we can't tell them apart, we're effectively forcing their home qubits to synchronize too. By measuring the light together in the middle, we cause an instant, shared link to snap into place between the two distant machines. This is entanglement. We have managed to use light as a bridge to force two physically separated, ultra-cold environments into a shared quantum state, all without the two systems ever physically touching. Historically, achieving this connection was incredibly difficult. The translation process is complex, and losing even a single photon as it travels down the cable meant the entanglement failed. Recently, researchers have upgraded the hardware inside the transducers. They are also using clever timing strategies, sending the signals in highly precise, staggered time slots, which helps them filter out ambient noise and correctly identify the quantum data. These upgrades are pushing the success rates of the connections to near-perfect levels. The entanglement between remote fridges is becoming reliable enough that we can start planning for real-world engineering, rather than just lab experiments. Once you can reliably connect two quantum computers across a room, you can connect them across a city. We can begin using the existing global web of fiber optic cables to weave dozens of isolated processors into one massive, synchronized system.